What we do in today's class is we look at the spectrum bands that are defined or kind of identified for 5G operations. And also, if the time permits, we look at what is 5G system architecture and what are all various components and their functionalities. Okay. So what has been done over the years is a lot of spectrum has been kept on added for providing these mobile services like 2G, 3G, and 4G. If you look at in the last 30 plus years, we have been using the spectrum all the way from 400 megahertz all the way up to 6 gigahertz for operating 2G base stations, 3G base stations, and 4G base stations. So what has been done as part of the 5G is rather than all the time allocating new spectrum, very often what has been done is we do something called a spectrum or band reforming, which basically talks about reusing the same bands which were earlier earmarked for 2G, 3G, and 4G, also for 5G. That means an operator who currently has a band for operating, let's say, 4G base stations, they can take another permission from the regulatory bodies to replace their 4G base stations with 5G base stations. Sometimes it is just a formality to inform that they are replacing their 4G base stations with 5G. Sometimes the regulatory bodies may charge additional licensing fee because they may think that operators started going to get additional revenue because they are going to provide a varied set of services to the users and other businesses who are planning to use 5G services. So that way, here what I'm trying to talk about is first let's look at 4G, that is LTE. It has around 51 bands. These bands can be used also for 5G operations. That is one important point. So that is called spectrum reforming, where we can use it. And in addition to these 51 bands of 4G, a lot of new spectrum bands have been defined for 5G operations. Very recently in 2019, ITUR had a conference that is called WRC, I think which stands for Wireless Radio Communication Conference, which happens every 4 years. Next one will be held in 2023. Previous one was in 2015. Every 4 years, ITUR conducts these kind of conferences where they agree upon what should be the spectrum that should be earmarked or how we can reuse the existing spectrum for new IMT services. Here I'm using the word IMT. So whenever I'm using the word IMT, it could be 2G, 3G, 4G, 5G, and beyond. That means it could also include 6G. So all these are kind of cellular networks or mobile networks which are meant for providing wireless wide area coverage. That's what the ITUR kind of looks at. It basically looks at which spectrum should be allocated and how they should be used across different countries, so that if some user is roaming across these countries, they should be able to see their handset working without you replacing the handset by just getting a mobile subscription service or the roaming agreement with the operator who is operating services in those countries. So that is the kind of job that ITUR does as part of these WRC conferences. So let's look at what has been done in November 2019. They have been kind of agreed upon to have two kind of frequency ranges for 5G operations. One of them is called FR1, that you are seeing it here. Other one is the frequency range 2. And you can see approximately it is spanning all the way from 450 megahertz to 6 gigahertz. A lot of bands in these radio spectrum have been earmarked for 5G operations. That is one thing, where some of them are like existing 4G or 3G or 2G bands. Some of them are newly added. So that is one important thing. And right hand side, what you see is the FR2, which is basically meant for millimeter wave operations, where you're talking about the spectrum starting from 24 gigahertz onwards for 5G operations. So this spectrum, which is in FR2, which was never used for any kind of wireless communication services, at least for terrestrial radio services or terrestrial wireless services. we were using only the FR1 for different kind of technologies, all the way from cellular to Wi-Fi to Zigbee, Bluetooth, and other kind of technologies, which include both licensed spectrum and unlicensed spectrum. So let's look at the bottom how different countries have allocated various amount of the spectrum for these 5G operations. You see, uh, there are different spectrum bands which are all in the range of 24 gigahertz onwards, and you can also see some spectrum band which is sub 6 gigahertz. For example, India and China are kind of planning to use this spectrum band spanning from 3.3 to 3.6 gigahertz, which basically give you the channel bandwidth of 300 megahertz for 5G operations. So this comes under FR1 range, whereas this one comes under FR2. So like that, in WRC 19, different countries and different regulatory bodies which represent those countries, they said that, okay, they are willing to earmark this spectrum for 5G operations in those countries. So, and again, they have to kind of agree upon or kind of have to have a consensus about what spectrum should be available. What is importance of having this kind of harmonization of the spectrum across different countries? By having a common bands across different regions, we can greatly simplify the complexity of the handset. For example, if all the countries, let's say, decided to use 3.6 to 4.2 gigahertz spectrum for their 5G operations, as you see clearly, even though different regions are using the spectrum ranging from 3 to 4 gigahertz, the actual band is varying. For example, if you look at Korea, it is 3.4 to 3.7. So you see a slight misalignment between the spectrum allocated in Japan and Korea for their 5G operations. Similarly, you can see there is a difference in China and India, where we are talking about using 3.3 to 3.6. And also, you see Europe 3.4 to 3.8. And I think here you are not seeing anything that is specific to sub-6 gigahertz here. But you can see, even though they are kind of very close, they are not exactly the same. I2UR, as part of this WRC conference, does is they try to convince all these different countries to be able to provide almost the same spectrum bands for the 5G operations. That way we can able to have a global roaming service with low-cost handsets realized. And on the right-hand side, what you see here are the names for the different bands which have been defined for 5G operations. They are numbers with the prefix N, where here N stands for NR. Basically, it means that these are the bands for 5G operations. And if you look at even in this illustration, look at this one. So this is one of the bands starting from 66 gigahertz to 76, having channel bandwidth of 10. Yeah, it is having a channel bandwidth itself has 10 gigahertz. It is really extremely high channel bandwidth that we are talking about. Here we have channel bandwidth of 5 gigahertz. And when it comes to sub 6 gigahertz, we are talking about, look at, see, we are talking about channel bandwidth, which is at 200 megahertz maximum. So that way, you can see there is a wide variation in terms of the channel bandwidth across these bands, which are spanning from 450 megahertz all the way up to 100 gigahertz out there. So after this, I2UR has kind of defined these are the frequency ranges for FR1 and FR2. 3GPP also has kind of taken up these spectrum bands, and they have conducted also lots of studies to see what could be the path loss and what could be the appropriate transmission power and whatnot for handset and the base station to operate. So they also finally agreed upon, and these are the finally standardized frequency ranges for FR1 and FR2, where FR1 is from 410 to 1725 megahertz. In FR2, it is 24.2 gigahertz to 52.6 gigahertz spectrum. So that we are talking about really an enormous amount of the spectrum, especially in FR2, because it is in the millimeter wave spectrum that is going to be added for 5G operations. And one important development here is even though we are talking about all the way up to 7.1 gigahertz, if you look at the previous slide, I'm showing you only up to 6 gigahertz because recently US has earmarked the 6 gigahertz spectrum entirely for Wi-Fi operation. So that way, that means 6 to 7, 6 gigahertz to 7 gigahertz. It has happened very recently. So they have earmarked for Wi-Fi. So because of that, cellular, especially when you don't want to have any interference, you should not be using it. Of course, we also have another variant of 4G and 5G called LTE in unlicensed and also called NR in unlicensed, where we can also deploy 4G and 5G base stations in unlicensed band, which are supposed to coexist with Wi-Fi access points. By default, Wi-Fi access points are designed to coexist with only other Wi-Fi access point in your vicinity. And as part of 3GPP standardization efforts, they have done a lot of work to make Wi-Fi base stations and 4G and Wi-Fi access points and 4G and 5G base stations to coexist with each other with minimal amount of the interference and share these unlicensed spectrum for the common good that is out there. But in general, this 6 to 7 gigahertz is not available in some of the regions as of now. So we have not seen how other countries are going to decide about this particular spectrum. That's the reason why very recently 3GPP has conducted a study about what are all the characteristics of the spectrum from 7 gigahertz to, as you see here, so 7 to 24. As of now, ITUR has not designed or not defined to use it for 5G operations. That's why we use the word sub 6 gigahertz, which spans up to 6 gigahertz. But 7 to 25, as of now, they have not identified. But very recently, what happened as part of the WRC 19 is they decided to include 10 gigahertz spectrum, which is coming somewhere down in this particular range, as one of the candidate spectrum for 5G as part of the upcoming WRC 23 conference. But otherwise, as of now, there are no countries. They have earmarked this spectrum from 7 to 24. But 24 onwards, as you see, it is millimeter wave, which offers extremely high bandwidth, but very poor coverage in terms of 50 to 100 meters. So this slide showing you in a nutshell various bands that are out there for 5G operations, where you can see there are 3 tables. If you observe very carefully, there are a lot of things that are being talked about. You see the word LTE reforming bands. So these are traditionally LTE bands, which have been again repurposed for 5G operations. So LTE has the band numbers all the way from I think 1 to 60 or 70. So by adding prefix N to the LTE bands, we'll get 5G bands. That way N1 is nothing but LTE band 1. So N41 is nothing but LTE band 41. So same bands with the same channel bandwidth can be also used for 5G operations. And also this table show you a lot of other details, but at high level, what you have to pay attention to here is let's look at in a simplistic terms, this N1. So here I'm talking about 5G NR band N1, which can be configured in 3 different modes, which is defined here in 3 different rows. One is with the sub carrier it is called subcarrier spacing. SCS stands for subcarrier spacing. So I will talk about what all this in the later, but at high level you can assume that this particular band can be configured with channel resources in 3 different manners, with a spacing of 15 or 30 or 60. Depending on which spacing that you use it, an operator can deploy 5G base stations where the base station can be configured with a channel bandwidth of 5 megahertz or 10 megahertz or 15, 20, all the way up to, you can see, 100 megahertz. Whereas in the case of N1, it is possible to configure base stations with channel bandwidth with maximum up to only 20 megahertz. But if you look at N41, which also has 3 different subcarrier spacing to define the waveform, can be configured with 10, 15, 20, 40, 50, 60, 80, 90, and 100. So that way, operator, whoever wants to go for providing extremely high data rates, they have to acquire appropriate amount of the spectrum from the regulatory bodies, and they can configure the base stations with 10, 15, 20, or 40, or 60, or 80, or 90, or 100 megahertz. As you've seen from Shannon's channel capacity, higher is the bandwidth, higher is the data rate that you can achieve in your system that is out there. So that is the significance of the subcarrier spacing and all other things. And the middle table that you have, it is showing you the new bands that have been added. Again, these bands are also up to 6 gigahertz only. Where you can see N77. This basically I'm showing only an example. Otherwise, as 3GP has defined N1 to N95 as the bands for 5G operations, where all these N1 to N95 as of now are having frequencies less than up to 6 gigahertz spectrum. And interestingly, you can see here as part of the middle table, we have again 15, 30, and 60, and the different configurations. Similarly, as you see here, the maximum here is 100, and here also it is up to 100. But finally, when it comes to millimeter waves, so as of now, 5 bands are defined. I'm showing you 4 out of the 5 in this table. So these are having number N257 to N261. There you can see there are 2 subcarrier spacing, where the minimum bandwidth itself is in the order of 50 megahertz, and the maximum can go up to 400 megahertz. That means operator can deploy a base station with a channel bandwidth of 100 megahertz. That is in FR2, whereas in the FR1, depending on whatever the band that you use, you can have the options up to 100 megahertz as your channel bandwidth. So let me show you quickly these channel numbers. Again, I hope you are able to see my screen here. So I'm showing a Wikipedia page here. So this is showing you all different bands for 5G operations. So the numbers that I was talking about earlier. So let's look at this particular thing here. So basically N1 is the band name, okay? And the duplexing mode, as you see here, we are talking about how the uplink and downlink are separated. So we have seen how in GSM we are using FDD and how cordless phones use TDD. So this band N1, whoever takes the license from the regulatory bodies can use to configure in duplex mode of FDD. That means you allocate separate spectrum for uplink and separate spectrum band for downlink, where the carrier frequencies are in the order of 2100 megahertz. And there's also a common name for this band that is called IMT. IMT is a very generic term, as I was mentioning, for all mobile or cellular systems. So this is the actual range for the uplink, and this is the corresponding range for downlink, where you see the duplexing space. That means downlink and uplink are separated by 190 megahertz. That means to a handset, you can assign the uplink frequency, let's say, as 1920. And the corresponding downlink frequency that you will be assigning is 2110. So which are separated by 80 plus, okay, 1920 means it is 80. Yeah, so this is 110. Yeah, so it is 190 is the spacing between downlink and uplink channels. So we have seen something similar in the case of GSM as well, where there's a spacing so that the uplink and downlink channels, when the handset is transmitting, don't interfere with each other. And these are the different combinations possible for the operators, where they can configure their base stations all the way from 5 megahertz to 50 megahertz. You may be getting, should be getting, I'm expecting some of you may be getting doubt. Can you tell me what is the channel bandwidth that you see it here? How much is available here? What is the uplink bandwidth?
60, sir.
And the downlink?
Same, 60.
60. So that is total how much we have? Total, the band N1 has 120 megahertz. Am I right?
Yes, yes.
So do you agree? The band N1 has a total of 120 megahertz channel bandwidth, which is equally split between uplink and downlink. Where in the uplink we have 60 and downlink we have another 60 megahertz. But when it comes to the configured channel bandwidth, I'm showing you maximum up to 50 and the least one is 5 megahertz. What is the meaning of this? Can somebody guess why there is a difference between these numbers that you see, which we use to configure the base station, versus the uplink bandwidth and downlink bandwidth? So are you able to understand my query at least?
So can you repeat that? I missed due to network lag.
Okay. So what I'm asking is, we have 120 megahertz as the channel bandwidth on or in band N1, whereas when you look at the channel bandwidth that are configured at the base station, it is ranging from 5 megahertz to 50 megahertz.
So I think
base station one is like for a single user you can allocate from 5 to 50, whereas this is like for entire communication you have to allocate between this band for whatever devices you have.
So what you are saying is 120 megahertz is assigned to the base station and 5 to 50 megahertz are assigned to the users. That's what you are saying, right?
I mean, like for a single user, like they can allocate from 5 to 50 at max 50. And for all of the user combined, they can allocate this 60 megahertz.
So that way you are kind of assuming that an operator, whoever want to provide, let's say 5G services, they have to take permission or they have to get the license for 120 megahertz if they want to use band N1. That's what you are implying, right?
Sir, is some frequency allocated to guard bands?
Yeah, of course, all of them going to happen. Guard bands are there and all other things, but those are like a kind of minor things. I'll ignore that. So the point I was trying to convey here is maybe okay. Let me open. I don't know why every time it will go to the, okay. So the example that I was talking about is with N1 is having 60 plus 60 for both the downlink and uplink. So what actually happens is, see, N1 is the thing that has been kind of defined by ITU, or basically it is a kind of, they kind of standardized that different countries can choose to decide and allocate N1 as the band for, let's say, 5G operations, which has the bandwidth of 120. So let's say assume that India has decided to earmark band N1 for 5G operations. So take this example. Because IT only says what are all different bands that can be used for 5G operations, but it is up to the countries to decide whether they want to really earmark those bands or not. So in this example, I am saying India has kind of decided to go and let different operators win this particular spectrum as part of the auction. But the important point you should make note here is no single operator is given entire N1. So that way, this 120 megahertz that you see it here. So maybe okay, I'm talking about 60 plus 60. Okay, so this can be divided into chunks of 5 megahertz. And when TRAI, our Telecom Regulatory Authority of India, when TRAI under DOT does a auctioning of the spectrum, they actually decide what is the base price for each of these 5 megahertz chunks. And they also put cap on how much an operator can acquire for different telecom regions and other things. I think India has around 22 or 23 telecom regions, where if we wanted to decide to acquire spectrum, you can decide out of these 23 regions, in which regions you want to acquire a spectrum like that. So what really happens is, we are not going to allocate the entire N1 band for one operator. An operator who is having a lot of capex and whatnot can decide to get more than one 5 megahertz band. So let's say somebody can take 20 megahertz, or other operator may decide, let's say this could be Geo, and BSNL may decide to go with 10 megahertz for AP circle. AP circle includes both Telangana and Andhra Pradesh. So this could be one possible configuration of the spectrum for two different operators. So finally, I'm talking about this example where BSNL has decided to use 10 megahertz. So this 10 megahertz is the one that is configured on the base station. So base station is configured with this 10 megahertz. And somebody was trying to say about how much is the bandwidth that is actually given to the user. So it all depends on something called resource blocks. So that I will talk about later. So the allocation of the resources to the users is done at the granularity of the resource block, where a given resource block typically having a size of 180 kilohertz. Of course, I can allocate n such resource blocks. N could be even 10 or 100, so depending on the capability of the handset. But this is the granularity at which you allocate the spectrum out of the 10 megahertz that is configured at the base station. So that way, if you round it off to, let's say, 200 kilohertz, okay, as an example, and if some operator is having 10 megahertz spectrum, so how much it will be? So this is 10 to the power of 7. So am I right?
Yes, sir.
So this is how it is done typically. Of course, it's not specific to 5G, what I'm talking about. Even in 4G, we do something very similar. So let me come back to this one. So you can see similarly other bands that are defined, like you can see. So let's look at some of the bands that you should be seeing here. Look at band 40 and band 41. So this band 40 is having the range from 2300 megahertz to 2400. It is basically the spectrum that is very close to the Wi-Fi. Wi-Fi operates on 2.412 or 2412 megahertz spectrum to 2600 or so. So this spectrum band is very adjacent to the Wi-Fi band, and this is the other side of the Wi-Fi. If N40 is left-hand side of the Wi-Fi spectrum, N41 is the right-hand side of the Wi-Fi spectrum, where again you can see the ranges of configuration where the operator can allocate. And you can see, okay, let's look at 90. So 90 is a special case, you can see clearly. Here I'm talking about TTTD operation, where uplink and downlink are not separated using different carrier frequencies. Instead, they are separated by allocating different time slot in same TDMA frame structure. So that is the case. And you can also see there are some other names. SUL, that stands for supplemental uplink. There is also called SDL. I think that will be there somewhere. Yeah, supplemental downlink. So these two are kind of a special bands where we are talking about something called dual connectivity, where your handset is connected with two base stations. One base station could be 5G base station, other base station could be 4G base station. If that is the case, the 5G base station can be configured to use this N76 band, where the 5G base station, which is acting as a supplementary link, can transfer the data to the user, or can transfer the data to the user using the bandwidth of 5 megahertz here. Similarly, you can see supplementary uplink here. So similar configuration of dual connectivity, where here the handset can send data to the supplementary base station that is deployed along with the regular base stations, where your handset can be allocated resource blocks by configuring the supplementary base station either at 5, 10, 15 or 20 megahertz. So like that, you can see there are tons of different bands. It's not that a country has to earmark all these bands for 5G operations. This is basically kind of a combination of all the things that have been agreed as part of this WRC conference for 5G services. That is kind of thing. And also there's something you can see here. Okay, let's look at this example. N2 is ranging from 1850 to 1910. But actually, this N2 is a subset of band N25. Let's look at N25, then you will understand what I'm talking about. Look at N25. N25 is ranging, the uplink is ranging from 1850 to 1950, whereas N2 is ranging from 1850 to 1910. There is a difference of 5 megahertz between N2 and N25, whereas N25 is a kind of a superset of N2. So this could be the case, like there are two different countries which have kind of decided to allocate slightly different set of carrier frequencies for their 5G operations. Then even though frequency range is more or less the same, they will be given entirely different band numbers. That way, all these N1 to N95, these are not mutually disjoint frequency ranges. Some of them are overlapping with each other. A given country can decide to use some of them depending on how their other spectrum, they wanted to use it for other kind of services like satellite services or their military operations or deep space networks or whatnot. Finally, you can see here at the bottom the frequency range too. As I was mentioning, there are, as of now, in WRC 19 meeting, they have decided to have these. Okay, there's one more. I see it here. Maybe this is an update, but in 2019 meeting, they decided to have these 5 up to N261. Now I see there's one more band that have been earmarked here. So all these are in millimeter wave spectrum. You can see the carrier frequency is in the order of 28 gigahertz here, where we have the channel bandwidth all the way up to 400 megahertz possible, where a base station can be configured up to this. But if you look at the bandwidth wise, for example, if you look at here, the band 260, it is having 3 gigahertz spectrum bandwidth. The channel bandwidth itself is 3 gigahertz, but we are not configuring base station with the 3 gigahertz. We are configuring the base station with maximum of 400 megahertz, but also there's a talk that in future this number also is going to be increased further from 400 to 800 megahertz as well. But as of now, it has been decided to go up to only 400. If you recall our discussion on Wi-Fi, where I was talking about 8.11x, that is called also as Wi-Fi 6. There we can have the channel bandwidth up to 160 megahertz. But again, the Wi-Fi bandwidth are all in the range of up to 6 gigahertz only. But since here we are talking about the millimeter wave, we are talking about the bandwidth of this high magnitude. But the comparison with Wi-Fi will be fair when you talk about the bands up to N95, where you can see the maximum of 100 megahertz. That means in Wi-Fi, when we have 160 megahertz as the maximum channel bandwidth, in the case of 5G, the maximum channel bandwidth is only 100 megahertz. But there's also another concept called carrier aggregation, using which operators can take 2 different bands, like an operator can have multiple such 100 megahertz channels, and they can join them together to offer, let's say, channel bandwidth of 200 megahertz as well. So that is also possible in 5G and also in 4G. In 4G, they do 20 plus 20 and 20 plus 20 plus 20 to get a multiple of 20 megahertz for offering 4G services. So any doubts or any comments on this slide? I will move on. So this slide, again, I'm just flashing the same slide. Here what you see is the first table showing you the band that have been reformed by using 4G bands. And the second table is showing the new bands, again in the range of FR1, that have been added for 5G operations. The bottom table is for millimeter wave, where we are talking about the frequencies in the range of 24 gigahertz for 5G operations. So any comments or any queries on these tables?
Sir, what is a SES?
I was mentioning in the beginning, it is called sub-carrier spacing.
Okay.
So this I will talk about when I'm going to talk about something called numerologies. If I have to tell in relations with 4G, in 4G we had only one fixed sub-carrier spacing, that is 15 kilohertz. What has been done as part of the 5G is, you can see the sub-carrier spacing has been increased from 15 to 30 to 60 to 120 megahertz. And why this has been done, all that is to support these URLLC and other kind of services. I was talking about low latency and mission critical services, which demand extremely low latency. So there, these subcarrier spacings are going to play a bigger role, where in 5G, there has been something called subframes and whatnot, where the number of symbols in a given frame are fixed, or in a given subframe are fixed. But the scheduling can be done at the granularity of millisecond or fraction of millisecond as well. So I will talk about what is subcarrier spacing and all later when I'm going to talk about the physical structure of the 5G networks. But for timing, you can assume that it is possible to configure 5G base stations with a different subcarrier spacing. By doing that, operators can provide different kind of services like EMBB, URLLC, massive MTC.
Okay, understood. Understood.
Okay. So again, let me show you the classification of the 5G spectrum based on the frequency that we use. So we can classify them as low, mid, and high bands. Low bands means the bands which are sub gigahertz, like less than 1 gigahertz, which can be used for mobile broadband. That's what we have been doing as part of 3G and 4G. This spectrum already we are using it for mobile broadband, but we can also use this band also for IoT services. So one advantage of using the sub-gigahertz spectrum is because the frequencies are low, the path loss is also less. Because other signal can reach easily hard to reach areas like undergrounds and other hard to penetrate regions. So especially when you want to deploy IoT devices at all these different locations, this spectrum band is extremely attractive. Even with the limited transmit power, we can able to reach these locations and we can able to significantly improve the battery lifetime. But of course, you may not able to provide high data rates, which is not the requirement for IoT, where we have the channel bandwidth maximum up to 50 megahertz. So, okay, when we use this. The second one is called mid bands, which are in the range from 1 to 6 gig, which can be used for both enhanced mobile broadband, that means more than what you can get with low bands, we can get with mid bands. And also we can use it for mission critical applications where we can give the maximum bandwidth up to 100 megahertz. So third one is the high bands, which is nothing but millimeter wave spectrum, which offer you extremely high data rates by giving you the channel bandwidth up to 400 megahertz even. Again, I was mentioning earlier, especially these millimeter wave bands have extremely challenging propagation characteristics because they require line of sight communication between sender and receiver, and the entire coverage region itself is very short. It is kind of comparable with what you get with Wi-Fi, which is in the order of 50 to 100 meters. That way we use these high bands for indoor scenarios like hotspots and other regions where you have a lot of user density and you wanted to provide high data rates there by deploying these small cells kind of thing. And one of the development recently here is FCC, which is a kind of takes care of all the spectrum allocation in USA. They have opened up 11 gigahertz spectrum band for commercial operations in USA. So this is in the millimeter wave spectrum, and all these spectrums are kind of taken up to this WRC 19 conference where they kind of agreed upon to open up this spectrum for 5G operations. So one of the killer application of using these high bandwidth is something called fixed wireless access, which is called FWA, okay, which is kind of meant to solve these last mile problem associated with fiber deployment in rural regions and also in hill regions. Let's look at what is that in the following slides. But we have one more classification based on the usage of the spectrum. So as I was mentioning, the spectrum can be allocated in general in two manners. One is license spectrum, for which the operators have to get license from the regulatory bodies by paying the spectrum royalty or fee for certain number of years, 5 years or 10 years or 20 years, where only the licensee can operate their services on that particular spectrum band. The second one is unlicensed, which all of us familiar with, where Wi-Fi, Zigbee, Bluetooth, and all industrial, scientific, and medical equipment generate their radiation in. Finally, very recently, there's a lot of studies that have been done in efficiently using the spectrum. So what happened is, even though some operators, especially the operators who offer terrestrial TV services, of course, in India it is not that popular. We have only Doordarshan, which is offering terrestrial television service. But in other countries, they have more than one such national broadcaster which is providing terrestrial TV service. Like in USA, if you look at, they have Fox News, ABC, and there are so many other channels which provide terrestrial TV service. But what is happening is these terrestrial TV services are typically deployed only in regions where we have high human populations. Otherwise, it is a waste of their investment, right? Of course, same thing is true even in the case of deployment of the cellular base stations as well. But what is happening of late is the spectrum, which has been earmarked for some of the applications like Doordarshan or for that matter for military applications, have been found to be not effectively used over the years. For that reason, a new way of spectrum sharing has been proposed very recently, that is called shared spectrum, where the spectrum can be used by both licensed users and also by unlicensed users. It is quite interesting. And a recent development in this context is again FCC has earmarked 150 megahertz in 3.5 gigahertz spectrum band, which they call it as CBRS band, which stands for US Citizens Broadband Radio Service, can be shared by different people for providing different services using something called spectrum access systems, SAS. So there are three kinds of users for this CBRS spectrum band. The first one are the kind of legitimate users like federal and non-federal incumbents like the military and broadcasters. I was mentioning, right? These are the guys who have been using or who were allocated the spectrum for specific activity. Like military may be using it for their tactical communication purposes. Broadcasters like Fox News and others may be using it for providing terrestrial TV service. But as I was mentioning, the usage by these incumbent users is very, very low. And in some regions, they are not at all even using it. So why to waste the spectrum when there is so much demand for the spectrum for providing connectivity and address the digital divide problem? Okay, so that's where the shared spectrum concept comes in. So in addition to incumbents, we can also let two other kind of users to use these spectrum bands. The second or the first user that can piggyback on this spectrum are the priority access licensees or the carriers, like operators like AT&T and others can also use this spectrum if it is not currently being used by military people and the broadcasters in the region where AT&T want to apply or provide the 4G services, for example. And the second category of the user that can also use the shared spectrum are the general authorized access users or the consumers. For example, in your home, you can actually deploy a Wi-Fi access point, which can be configured to use the CBRS band, which is having the channel bandwidth up to 150 megahertz. So what is the significance here? So this is the order in which you can use it. First, we have these incumbents. If the incumbents are not using, then carriers can use it. Both incumbents and the carriers are not using it, then consumers can use the spectrum for their in-house Wi-Fi services. You can also watch this nice YouTube video. This kind of explains the significance of this CBRS band and how this is going to be a kind of a new revolution in terms of the way spectrum can be used for different kind of wireless services. So I was just mentioning about something called spectrum access systems, which are kind of required for sharing the spectrum by these secondary and other people. As I was mentioning, the carriers and generalized public who wanted to reuse the shared spectrum, which has been earmarked for the incumbents. How this can be done is like this. So let's look at this example. Let's assume that this is a US Navy. We have been earmarked some other spectrum in that 3.5 gigahertz range. So as you see here, these Navy ships, again, they go over the ocean and sometimes they come to the shores. So the challenge comes when they're coming to the shores, because at the time when they wanted to use their spectrum band, there's also chance that the users who are kind of in that seashore, if they also are using the same spectrum, then there's a lot of interference. So what is needed is something kind of a sensor network, where the sensor network, which is deployed, let's say on the seashore, let's assume that on the seashore, we have deployed the sensor network. The job of the sensor network is to detect the RF radiation in the CBRS band. Basically, it is like kind of a, what you do, we are doing something called sensing. So it is very similar to the way you use the Wi-Fi radio and keeping it in the monitor mode to listen to what are all the packets that are happening in Wi-Fi spectrum. But here we are not talking about any specific wireless technology. You are just deploying a sensor network with RF modules whose job is to listen to the CBRS spectrum and see whether they can detect any received power. That's all. This power could be belonging to any kind of waveform or any kind of wireless technology. That doesn't matter. Just checking whether spectrum is free or currently being used by these Navy ships when they are coming to the seashore. So this information is sent by these sensors to a centralized database. So we can assume a cloud-based setup where the information about the latitude, longitude, and whether the corresponding spectrum is currently being used or not. Only that information is kind of stored in these cloud database servers. Then we have these interested people like carriers and general public and whatnot who are interested in reusing the spectrum if this is not currently being used by the incumbents and also by the carriers. So how they have to do this is, whoever is interested to reuse the spectrum, they have to subscribe to this SAS system, that is spectrum access system. And it is a kind of a, you register, and whenever the system detects that particular spectrum is available or not available, that information to, let's say, this enterprise you want to deploy, let's say, Wi-Fi on the CBRS spectrum. Basically, what it simply means is that if you are deploying a Wi-Fi access point in the CBRS spectrum, you have to first query this particular SAS database and check in that particular region that spectrum is used by any incumbent or any carrier or not. If not, then this particular access point can be configured to use that spectrum for providing the Wi-Fi services. Similarly, once this Wi-Fi started operating, all of a sudden, one of the operators or one of the incumbents started using the same spectrum for their legitimate operations. This particular Wi-Fi access point will be notified that, okay, we have detected the presence of an incubator. You have to vacate this spectrum. Then this access point has to fall back to the unlicensed spectrum or has to find one of other bands which is also meant for speed access, which is currently free for usage. Like that, it is called something called dynamic spectrum access, DAS. So dynamic spectrum access, this can be done using this kind of a spectrum access systems where we are simply querying a database, but we can also think of Wi-Fi access point itself is provided with one sensor, which itself can detect the presence or absence of these incumbent people and accordingly inform the Wi-Fi access point to switch over to other channels whenever they detect the presence of incumbents. That is there, but to significantly cut down the cost of detecting the presence and absence of these incumbents, this kind of a centralized cloud-based database system has been decided. Federated Wireless is one such company that provides this kind of services for using CBRS band in United States. So if you wanted to have this spectrum for your operations in your neighborhood, you can subscribe to the service from Federated Wireless and start using CBRS band. So any comments or any queries on this part? Does it make sense what I'm saying?
Sir, hello.
Suranjan, go ahead.
Sir, this sensor network basically find out what is the frequency that this Navy is using, right? And then it is telling others not to use it. But
No, In other words, you can assume that this sensor network checks all the CBRS bands, and it checks whether the CBRS band is currently being used by the this military or not.
How will it understand whether the signal is used by Navy or some other person standing right beside it or something like that?
Yeah, you are right. See, because as you see, it is a clearly a special purpose sensor network. This has been designed to understand the waveforms that are being transmitted by these instruments. For example, if it is military, and let's say if it is like a 4G, then the sensor network is equipped with a corresponding radios where it will listen to those signals and detect the presence. Yeah, you are right.
Oh,
Yeah, it is a specialized sensor network. It is not like a very general purpose one. Yeah.
right, right. Okay.
Okay, so let me conclude this chapter or this class on 5G spectrum with one of the killer applications that have been talked about a lot when we are talking about 5G deployments to start with. So one of the motivation behind that is one of the survey told that only 50% of the households are going to get broadband services by 2023. So try to understand what I'm trying to say that only half of the households will get broadband line to their homes by 2023. So this is not the statistics for countries like India. So we are talking about for developed countries. For India, this statistic is even poor, maybe 10 to 20% or so. So that low is the penetration of the broadband. Whenever I'm using the word broadband, here I'm talking about a fiber to the home or ADSL line or the cable internet that you get to your homes from operators like Airtel, BSNL, Geo, Act Fiber, and others. So one of the challenges with providing this broadband connectivity is one has to bring an ADSL line or Ethernet line or the fiber line all the way to your home. So we have to kind of do this on top of the lamppost that you see in the figure, or you have to dig the ground and you have these fiber or the ADSL cables to get the connection to the homes. So because digging and doing all these kind of things using the lamppost is extremely challenging, that is the reason why even today the penetration of the broadband is very poor. But at the same time, all of us agree that the penetration of the mobile services like 4G and 3G is quite significant and much higher than the 50% that I'm talking about now. So now the question is, one of the motivation here is, can we use 5G to address this problem of providing broadband connectivity to the houses? So in 2018, Verizon has rolled out 5G home services in USA, where they wanted to provide data rates all the way up to 1 Gbps using the 5G as the last mile connectivity thing, where each house receives a 5G receiver and also a home router, in which the home router provides Wi-Fi access, and 5G receiver is the one that brings the data all the way up to 1 Gbps inside your home by eliminating fiber lines or the ADSL lines, which requires a digging or laying on top of the lampposts. So this particular 5G radio is supposed to be using the millimeter wave band, because here I am talking about wireless connectivity only, where, okay, let me show you the example. What is the system architecture here? Let's look at the system to better understand what I'm talking about. There are many components that you see it here. So this is the point from which the operator wanted to provide you broadband internet to your home. That it is a traditional approach. From this particular NGCO, we get a fixed network. There's a cabinet. So from that you will get the fiber access or ADSL. So this is called customer premise equipment. It is like a modem or a switch or a Wi-Fi access point or the router that is deployed at your home. So this is how all of us know getting the broadband line. But what you are seeing here is optionally using the 5G to get fixed wireless to the home. That is one case where I'm talking about this line becoming optional, or some operators also can think of, or some ISPs can also think of providing two lines. One line is like this using this fiber line, and other line is through the 5G. So that way you can get redundant connectivity to your home, so that your reliability of the connection can be greatly improved. Let's look at what is happening here from this head node. From here, we are having a backend connectivity to a 5G base station. So that's what, of course, nothing specific to the 5G. We can also do with 4G or even other kind of cellular technologies, but the example is showing with a 5G base station. Where you can look at this case, this base station, which is for 5G, and also again, the example is showing that we can use it also for IoT, but anyway, ignore that part. For timing, I'm showing you two cases where this 5G base station is connecting or offering the services to two different users. One user is the like your smartphone, mobile broadband user. Okay, it is directly connected with this outdoor base station of 5G. So we're using one beam. So there is another beam for fixed wireless access. So that's similar to the way you have a radio in your smartphone for 5G. So we can think of deploying another node. So that is the one that you see it on the lamppost. So this is the fixed wireless access user equipment. So the green box that you see it in this cartoon is the one that white box that you see that is mounted to this lamppost. So that way this lamppost, this box, this is nothing but 5G user equipment, similar to the way you have user equipment in your smartphone for connecting the base station. So exactly the way your handset connect to the base station, this fixed wireless access user equipment which is mounted to the lamppost is also connected to the base station. Okay, so that is the point. So then, so that way what we have kind of done is we have brought the 5G connection from the base station to this lamppost. But the house is here. Now we have to take the data all the way from this particular location to inside the house. So there are multiple choices that are possible. One example that you can think of is from here to here. That means from the lamppost to the customer premise equipment that is deployed inside the home. You can either think of using a fiber line, or you can even think of using another 5G link as well. Similar to the way that you think of, you can also have another point-to-point 5G link. Or you can even think of deploying a Wi-Fi access point, basically Wi-Fi in a peer-to-peer mode, like a Wi-Fi direct kind of thing. So there are multiple options, but I think in this particular example, anyway, it is not clear, but you can think of that they might have done that using some dedicated cable, like Ethernet cable. If it is less than 100 meters, you can lay all the way from here to the inside home, connecting to this customer premise equipment. So this customer premise equipment is typically come with the LAN ports and also with built-in Wi-Fi access point. Otherwise, you can also connect your external Wi-Fi access point. Then you have the Wi-Fi coverage inside your home, or you can think of this also having another SIM, using which you can also provide cellular services, where the cellular data from these devices will go first here, from then it will go here, from then it will go here. So like that, we are talking about fixed wireless access as a killer application for 5G early 5G deployments to kind of address this broadband connectivity problem that is there everywhere, not just developing countries, it is also there for developed countries. For them, the problem is a lot of geographical region with sparse population. So that it is economically not feasible for them to deploy the fiber because of lack of return on the investment that they make, especially for ISPs that I'm talking here. Okay, so any comments? Is that clear to all of you? How we can use 5G to bring internet connectivity inside homes?
So, sir, basically in 5G, we will be talking to a base station situated in our home premise rather than speaking to the tower directly.
So Ranjan, are you talking about this illustration or are you talking in
Yes,
general?
this illustration.
No, in this illustration, there is no base station next to your home. See, this is not the base station. Look at the
No, no.
on the.
Can we take this CPE as the base station and like all the devices are
Okay,
connected to
okay.
the CPE?
Yeah, yeah, that is also possible. Yeah, yes, yes. So that's exactly what I meant by small cells. If you recall, I was talking about uh, cellular small cells where we can deploy those indoor environment. Yeah, that is also an option. Yes, we can have CPE which create a cellular small cell. In that case, you can get cellular connectivity inside home, or you can think of CPE providing a Wi-Fi coverage inside the home. So either of them is possible. But if you look at putting Wi-Fi will be cheaper than putting again a 5G small cell, right?
Right.
Because as of now, if you look at the cost of the Wi-Fi access point is several times cheaper than the cost of even small cell base stations. Because even though we say small cell, they are not meant for home users. They are meant for enterprise deployment, like in hotel, shopping malls, where the operators themselves deploy these small cells. Still, they are kind of expensive devices when you compare them with Wi-Fi access points. That way, it is expected that we deploy only Wi-Fi inside CPE, but not the small cell. But again, nothing prevents somebody to put again a small cell inside CPE. That is also doable. Yes. Okay, so these are a couple of reference books that I wanted you guys to read for this particular chapter on 5G. The first one I was also mentioning earlier, that is the 5G mobile networks, a systems approach by Peterson and others. So this is available as a web version. It is I think it is a kind of an introductory book, but it gives you a very good overview of how the 5G systems are there and what are the system related issues without going too much into the underlying radio access network part of the 5G systems. That if somebody is interested more about how SDN, NFV and other things are playing role in 5G, this book is a very good starting point to understand what is 5G and how 5G is embracing all these technologies to offer high data rates. And the second book that is you see on the right hand side by Eric Dahlman and others. So it is going too deep into the 5G radio access networks. So that means here I'm talking about 5G new radio. This is exclusively talks about the connectivity between the handsets or basically the user equipment and the base stations. So what happens on the radio side? So all the protocols and all the waveforms and other things are being discussed in this book. So this book is not available freely, but you can read the sample chapters on Google Play. But if you want to buy, yeah, it is also available on Amazon and other e-commerce platforms for you to try. So these are all various reference link. I am not sure whether you have gone through or not. So yeah, so this is one link that I added today. So you can also try to go through this to understand these are different frequency bands for 5G, what is supplementary uplink and supplementary downlink. So any questions on the 5G spectrum?